Hello my dear students, only few of the elements can form coordination compounds, not all elements can form coordination compounds. You will understand this better when I explain this with the examples. What does Hund's rule tell? Every orbital should be singly occupied, then only the pairing up will start. But we need vacant orbitals. From where do we get the vacant orbitals? You understood now the difference between inner orbital and outer orbital? Hello my dear students, welcome back to the session 4 on coordination compounds. Today I shall teach you all about Werners theory and valence bond theory. There is one question which is sure shot going to come for your exam, which I have taught in this session. Last class we learnt about isomerism in coordination compounds. Okay? Today we will see what is Werners theory. Alfred Werner in 1898 proposed this theory. He prepared large number of coordination compounds, studied their physical properties, chemical properties and isomeric behavior using some simple experimental techniques. This Werners theory was the first successful attempt to explain the nature of bonding in coordination compounds. So, we will see what is this theory all about. The main postulates are the central metal atom or the ion shows two types of valency, that is primary and secondary valency. We will understand this better with an example. For example, if I take CuNH3 4 with Cl2. Okay. In this particular complex, I will first calculate the oxidation number of metal. Okay. So, I will take this as X plus amine ligand has 0 charge. So, 0 into 4, okay, plus chloride ion has -1 charge. So, it is -1 into 2 is equal to 0, X is equal to +2. Now, the oxidation number of the central metal ion is called as primary valency. What is it? Primary valency is equal to the oxidation number of the metal ion. Okay. Same way, you can also see here the copper metal ion is bonded to 4 amine ligands. So, how many coordination bonds are there? There are 4 coordination bonds, and the number of coordination bonds formed by the metal ion with the ligand is nothing but the secondary valency of the metal ion. So, secondary valency is the coordination number or the number of coordinate bonds which is there around the metal ion. Okay. So, we will see further. Okay. The primary valencies are ionizable and are satisfied by negative ions. Correct. See here, the metal ion has +2 charge and it is satisfied by negative ions, which is nothing but chloride, which is present as the counter ion. Why is it told as ionizable? Ionizable because if I dissolve this particular complex, I will get chloride ions in my solution. Hence, the ions which are satisfying the primary valency can be ionized, or when I dissolve they come into the solution. So, that is the second postulate. What is it? The primary valency are ionizable and are satisfied by negative ions. The next postulate is the secondary valency is non-ionizable. It is equal to coordination number of the central metal ion. It is fixed for a metal. For a particular metal, coordination number is fixed. Okay. Also, what is it? The secondary valency is nothing but the number of coordinate bonds or coordination number of the metal ion. Here in this case, the coordination number for copper is 4, okay, which is satisfied by 4 ligands. The secondary valency are satisfied by negative ions or neutral molecules. It can be negative ions or it can be neutral molecules, which is nothing but ligands. So once again, the primary valency is the oxidation number of the metal ion. It is ionizable and it is satisfied by the negative ions. The secondary valency is the coordination number of the metal ion. It can be satisfied by a negative ion or a neutral molecule, which is called as ligand. And secondary valency is always fixed for a particular metal, whereas primary valency is variable. For example, if we had iron metal atom Fe, iron can exist in 2 different oxidation state. That is, it can be in +2 state or it can be +3 state. That is nothing but the oxidation number for the metal. So oxidation number of the metal can be different. Okay, so primary valency is not fixed, it is a variable, but secondary valency is always fixed for a particular metal atom or ion. Okay. Next we will see primary valency is non-directional, whereas secondary valency is directional. Means the secondary valency is the one which is actually telling us about the geometry of the complex. Okay, you can see ions or molecules attached to satisfy the secondary valency have characteristic spatial arrangement. That means the ligands have a particular spatial arrangement and thus they will tell us about the geometry of the complex. Okay. Here once again I shall repeat, primary valency is nothing but the oxidation number of the metal ion. It is always satisfied by negative ions. Okay. And primary valency can be, it is variable, it can change from one complex to the other, whereas secondary valency is nothing but the coordination number of the metal ion and it is fixed. Okay, and coordination number is always satisfied, or the secondary valency is always satisfied by ligands. And secondary valency also tells us about the geometry of the complex. Okay. I shall take one more example to explain the postulates of Werners theory. In this particular example, you can see the primary valency of the complex is +3. Once again, I shall calculate here. I have cobalt with NH3 6 Cl3. Okay. The name of this complex will be hexaamine cobalt 3 chloride. Okay. And the oxidation number is X plus 0 plus minus 3 is equal to 0, X is equal to +3. This is the primary valency. The cobalt is attached to 6 ligands. So the secondary valency will be 6. Okay. The primary valency +3 is satisfied by 3 negative ions, and the secondary valency 6 is satisfied by 6 amine ligands which is there around the central metal atom. Okay. I hope you have understood about the Werners theory. As the coordination number is 6, this particular complex has got octahedral geometry. Okay. So, I hope you have understood about the Werners theory. Next, limitations of Werners theory. A few elements have property to form coordination compounds. Only few of the elements can form coordination compounds. Not all elements can form coordination compounds. Why? Werners could not explain. Also, the bond in coordination compounds have directional properties, that is, the secondary valency is satisfied by the ligands, and the ligands have a particular spatial arrangement, isn't it? That is why they are directional in nature. They have a particular exact arrangement which is giving rise to geometry for a particular complex. Why exactly that is happening, Werners could not explain. Also, coordination compounds have characteristic magnetic property, optical property, also has color as well. Okay. All these three Werners could not explain. So, these are the limitations of Werners theory. Next is valence bond theory. Valence bond theory explains the nature of bonding. Also, it explains about the magnetic property and geometry of the coordination compounds. The central metal atom or ion requires vacant d orbitals which will undergo hybridization to bond with the ligands. Okay? That is, see here, the central metal atom or ion under the influence of ligand can use its n-1 d ns np or ns np nd orbital for hybridization to yield a set of equivalent orbitals of definite geometry. So, what it told? There is vacant n-1 d orbital, ns orbital and np orbital or ns np nd orbital. So, what do you understand here? The vacant orbitals in the central metal ion undergoes hybridization, okay, under the influence of ligands to give rise to new orbitals, okay, new hybridized orbitals of definite geometry. Okay. Also, these hybridized orbitals are allowed to overlap with the ligand orbitals that can donate a pair of electron. Now, these hybridized orbitals are vacant, okay, that will overlap with the filled orbitals of the ligand to form the coordinate bond. Next, it is possible to predict the geometry of the complex and the magnetic behavior. From valence bond theory, you can actually tell the geometry of the complex as well as the magnetic behavior. If you are still having some doubts with the postulates, you will understand this better when I explain this with the examples. Okay? Here you can see, if you know the coordination number and type of hybridization, you can tell the geometry of the complex. Okay? If the coordination number is 4 and the hybridization is sp3, we can tell the geometry is tetrahedral. If the coordination number is 4 and the type of hybridization is dsp2 hybridization, then you can tell the geometry of the complex is square planar. If the coordination number is 5 and if the type of hybridization is sp3d, then the geometry will be trigonal bipyramidal, and if you have coordination number 6, there can be two types of hybridization, sp3d2 or d2sp3, but the geometry will be same, that is octahedral. More detail about the coordination number 6 and coordination number 4 we will be learning further. Okay. So, the first example for octahedral complexes. Example what we are taking is CONH3 6 3 plus charge. It is a cationic complex. Okay. Now, the electronic configuration of cobalt metal atom is argon 3d7 4s2 because it is having the atomic number 27. Okay. In this particular complex, the oxidation number of cobalt will calculate. Here you have to take cobalt as X plus amine it is 0 is equal to plus 3 because it is having the charge plus 3. So, X is equal to plus 3. Thus, orbitals of cobalt in plus 3 ion I am going to represent. Okay. That means from here this is for the cobalt atom, but in my complex cobalt is present in plus 3 state. So, we have to remove 3 electrons, 2 electrons from s orbital, 1 electron from the d orbital. So, we have 6 electrons in the d orbital which is left in cobalt plus 3 ion, okay, which I have represented here 1, 2, 3, 4, 5, 6. 6 electrons in the d orbital. Now, next step what we are going to write? We have to show or we have to talk about the hybridization. I have the central metal ion that is in cobalt plus 3 state. Now, when the ligands approach this central metal ion, the ligand here is amine ligand. It is a very strong ligand. When these ligands approach cobalt plus 3 ion, what happens is the electrons which is there singly occupied in the d orbitals will start pairing up against Hund's rule. What does Hund's rule tell? Every orbital should be singly occupied, then only the pairing up will start. But when the ligands are approaching the central metal ion, these electrons will start pairing up against Hund's rule. Okay. So, you can see total 6 electrons because of the pairing. This will jump over here, this will jump here, and you can see I have paired up the 6 electron in the first 3 orbitals of I have paired up the 6 electrons in the first 3 d orbitals. Okay. You can see now the next 2 d orbitals are vacant. Next what I have to see is how many ligands are there. I have 6 ligands. That means every ligand is giving 2 electrons. Each orbital can take up only 2 electrons. So, how many vacant hybridized orbitals I require? If there are 6 ligands which are monodentate, okay, I will require 6 hybridized orbital to occupy the electrons which is donated by the ligand. So, how many orbitals have to undergo hybridization? 6, because there are 6 monodentate ligands. Okay. So, here you can see I have 2 vacant 3d orbitals, 1 4s orbital and 3 vacant 4p orbitals. So, I will count 1, 2, 3, 4, 5, 6. So, all these 6 orbitals will undergo hybridization. Okay. Which hybridization? I told you 2 d orbitals. So, d2, 1 s orbital s, 3 p orbitals sp3. So it is D2sp3 hybridization will occur. Okay. Once these hybrid orbitals will mix and form new hybrid orbitals, then it will overlap with the filled orbitals of the ligand, okay, which I have shown here. The electrons are donated by the ligands have been occupying the D2sp3 hybridized orbitals. How many D2sp3 hybridized orbital? 6 D2sp3 hybridized orbitals, which is filled now with the 6 electron pairs from NH3 ligands. Okay. Now, how do I predict the magnetic property? In the last step, if you see here, after the formation of the complex, can you find any unpaired electrons? No. You have all paired up. You can see here. First 3 it is paired up. The electrons, of course, it's giving 2 electrons each. All are paired up. As there are no unpaired electrons, magnetic property is diamagnetic. If there was an unpaired electron, then the magnetic property would be paramagnetic. As the coordination number is 6 and the hybridization is D2sp3, the geometry is octahedral geometry. Okay. Now, one more thing, if you observe, I have written inner orbital or low spin or spin paired complexes. This is an example for inner orbital or low spin or spin paired complexes. Why we have written it this way? You see the hybridized complex which is formed. During hybridization, the orbitals which is used up is 3d orbitals, 4s orbital and 4p orbital. The valence orbital 4s and 4p was used, but not d orbitals was not of the 4th shell, it was from the 3rd shell which was utilized. Correct? The d orbital which is used for hybridization was not from the 4th shell, it was from the 3rd shell, that is the previous shell. As it is used from the previous penultimate shell, okay, we call it as inner orbital. What do we call it as? Inner orbital or low spin complex. Okay. Also spin paired complexes, because of the ligand, because it was a strong ligand, what happened? There was pairing which occurred against Hund's rule. That's why it is also called as spin paired complex. Okay. As pairing occurred, we also call it as spin paired complexes. Why inner orbital? Because the d orbitals of the ultimate shell or the 4th shell wasn't used, of the penultimate shell was used, of the previous shell it was used, hence it is also called as inner orbital complex. I hope you have understood. We have the next example of same metal cobalt which is bonded with 6 fluorido ligands. First we shall again calculate the oxidation number. Okay. X plus minus 6 is equal to minus 3. So, X will be equal to plus 3. So, the oxidation state of the metal cobalt is plus 3. Okay. So, electronic configuration of cobalt atom is argon and 3d7 4s2 because its atomic number is 27. As it is in plus 3 state, we have removed 2 electrons from here and 1 electron from the d orbital. So, the orbitals of CO plus 3 ion is having 6 electrons in the 3d orbital. Okay. When the ligands are approaching the central metal ion, that is cobalt plus 3 ion, here spin pairing will not take place, or because the ligand is a weak field ligand, okay, it is a weak ligand, the electrons cannot pair up. The pairing up against Hund's rule will not happen. But we need vacant orbitals. From where do we get the vacant orbitals? Of course, after this you have many vacant orbitals. You need 6 vacant orbitals because we have 6 ligands. We can use 4s orbital, so 1s orbital, 3 p orbitals and d orbitals from the same shell, that is 4 d orbitals, not all the 5 we are using, only 2 orbitals of the 4d. Okay, so we are writing d2, correct. Did we get 6 orbitals? We will count again, 1, 2, 3, 4, 5, 6. So we have got 6 vacant orbitals which is undergoing which hybridization? sp3d2 hybridization. We have written d2 on the other end because the d orbital of the same shell was used for hybridization. Okay, that is why it is also called as outer orbital or high spin or spin free complex. You understood now the difference between inner orbital and outer orbital? I hope you have understood. We will move forward. Now once it has undergone hybridization, okay, now the hybridized orbitals of the metal will overlap with the orbitals, filled orbitals of the ligands, and the ligand will donate a pair of electron towards the metal ion, and those electrons fill up the hybridized orbitals. You have here 4s, 4p and 2 of the 4d orbitals are filled with electrons from F minus ions, that is fluorido ligands. Okay. Magnetic property, if you see the final structure once the complex is formed. There are 4 unpaired electrons, hence it is paramagnetic. If there are unpaired electrons, the complex is paramagnetic. If it is not having any unpaired electrons, then the complex will be diamagnetic. As the hybridization is sp3d2 hybridization, geometry is octahedral. I hope you understood both the octahedral complexes. Okay. One example we have for sp3d2 hybridization and the other example we have for d2sp3 hybridization. Okay. It is a very important question for your exam. This is for octahedral complexes. Next we are going to deal with tetrahedral complexes. Okay. First example, nickel with 4 chlorido ligands. Okay. Let us calculate the oxidation number of nickel. I have X plus chlorido ligands have -1 charge into 4 is equal to -2. Observe here it is an anionic complex. So, X is equal to +2. So, oxidation state of nickel is in +2 state. What is the atomic number of nickel? It is 28. So, its electronic configuration of the atom is argon 3d8, 4s2. As in this complex, nickel is in +2 state, its orbital will have 8 electrons. What is it? The 3d orbital will have 8 electrons. The 2 electrons are lost because it has got +2 charge. Okay. So, you can see 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons are present. Now, when the ligand approaches the Ni+2 ions, as it is a weak field ligand, chlorido is again a weak field ligand, because of which spin pairing will not happen. This remains as it is, but it requires empty orbitals. How many empty orbitals? 4 because I have 4 ligands which is monodentate. So 4 empty orbitals, 1 s orbital, 3 p orbitals. So it is sp3 hybridization takes place. Now sp3 hybridized orbital will of the metal ion will overlap with the filled orbital of the ligand to form coordinate bond. The electrons pairs from the chlorido ligands occupies the sp3 hybridized orbitals. Okay. Now if you observe the final step, in the final step you can see there are 2 unpaired electrons and thus it is paramagnetic, and because the coordination number is 4 and the hybridization is sp3, geometry is tetrahedral. Okay. I hope it is becoming a little easier now because we are doing the third example. Okay. We have one more left, that is NiCN4 2 minus. Okay. We shall calculate the oxidation state quickly. X plus minus 4 is equal to minus 2, x is equal to plus 2. So even in this complex, if you see nickel metal atom is having a plus 2 charge. Okay. The electronic configuration of nickel atom is argon 3d8 4s2. As in this particular complex it is having plus 2 charge, 2 electrons are lost and we have 8 electrons in the 3d orbital. You can see here 8 electrons in the 3d orbital of Ni plus 2 ions. Next what happens? dsp2 hybridized orbital of Ni plus 2 you have to show. Why it undergoes dsp2 hybridization? Because cyanido ligand is a strong field ligand. Because it is strong, these 2 unpaired electrons will pair up against Hund's rule, and you can see all the 8 electrons are paired up in the first 4 orbitals of 3d and 1 d orbital becomes vacant. We require 4 vacant orbitals. I have 1 d orbital from 3d, 1 s orbital of 4s, and I will take up only 2 orbitals of p because I require only 4 orbitals. What is required? Only that we are going to pick up. So dsp2 hybridization will occur. Now the hybridized orbital of the metal ion will overlap with the orbitals of the ligand to form coordinate bond, and the electrons from the ligand is filled up in the dsp2 hybridized orbital. So 4 electron pairs from Cn minus ligand. Okay. If you observe here, there are no unpaired electrons, thus it is diamagnetic, and because of coordination number 4 and dsp2 hybridization, geometry is square planar. What is it? Square planar. Now if you ask me how important these 4 questions are, it is very important. Why exactly? Because I told you all there is one short question which will come from this chapter, and it is this question. Out of the 4 examples which we have taken for VBT, that is octahedral complexes, we have 2 examples, and for tetrahedral complexes we have 2 examples. All the 4 are very important, and out of these 4 complexes, one is a short question for 3 marks for your exam. It can be question number 25 or 26 in your question paper. how do you write the answer? It carries 3 marks. So, it is very important that you write the electronic configuration, okay, of whichever complex they have asked. You write the electronic configuration of the metal ion, then show the orbital of the central metal ion and the filling of the electrons. Then you have to write about the hybridization. The next step, you have to show where the electrons from the ligand has filled the hybridized orbitals. That will carry 1 mark. Next 1 mark to write about the magnetic property. Another 1 mark you have to write about the geometry of the complex. So, all the 4 are really very important for your exam. Okay. Next class we learn about magnetic property and crystal field theory. Okay. I hope you have understood today's class. Stay tuned, stay focused. Thank you, my dear children.